Hey there guys, it's Mike coming back at you with another video on college algebra. In the previous video, we talked about the rectangular coordinate system, we talked about plotting points, distance between 2 points, midpoint of 2 points, graphs, plotting graphs, and intercepts amongst other stuff. In this video, we are going to talk about the difference between a relation and a function. So a set of ordered pairs x comma y is called a relation in x and y. Just a general set of ordered pairs. It can also be an actual equation, just like what we saw in the previous video, or it could be a visual representation of a relation through a graph. The set of all x values in the ordered pairs is called the domain of this relation, and the set of all y values in the ordered pairs is called the range of the relation. Big thing is domain is the set of all inputs, range is the set of all outputs that you have from your set of ordered pairs or your equation or your graph. For what we'll be doing in this course, we're going to be focused for the most part on functions, which are just special relations. But the key question is, when is a relation a function? Some of you may already know when a relation is a function, but in case you don't, a relation is a function when there is only one output or y value in the range for each input or x value in the domain. Basically, a relation is a function when one input only leads to one distinct output. If you have one input that gives you two separate outputs, two different outputs, then that is not a function. We say, if we have a function, we say that y is a function of x, and a way that we typically write this is to say y equals f of x. Y is a function of x. This is one of those kinds of things where all functions are relations, but not necessarily all relations are functions. We are going to see graphs of things that are relations, graphs of things that are relations but not functions, and graphs of things that are functions. So every function is a relation, once again, but not every relation is a function. There are three ways that we can analyze relations to see whether or not they are functions. As I mentioned, sets of ordered pairs, graphs, and then the other thing we're going to take a look at are things called maps. So kicking it off, if you're given a set of ordered pairs, you should be able to tell if the set of ordered pairs describes a function or not. So does this set of ordered pairs below describe a function? If it does, state the domain and range. So what we're looking at in this set of ordered pairs is mainly we're looking to see, are there any points where we have the same x coordinate? If there are points where we have the same x coordinate, do we have different y coordinates for those two ordered pairs, or do we have the same y coordinate showing up? If we have 2 points that have the same x coordinate but not the same y coordinate, then we do not have a function there. This is not, this set of ordered pairs does not describe a function. But if we take a look here, we have 5 ordered pairs, and the x coordinates on each of these 5 ordered pairs is different. From what we are seeing here, from the set of ordered pairs, yes, this does describe a function. So we have to state its domain and range. The domain, once again, is just the set of all x values or inputs of these ordered pairs. So -2, -1, 0, 1, and 2. The range is just all the y coordinates of these points, 1, 6, 7, and 11. Note that we had the number 1 showing up twice, and when we write it, and when we write out the range, we don't write the number 1 twice. If it's already in there, we don't have to write it a second time. Here's another one. This set of ordered pairs consists of the points -4, 0, 2, 1, 5, -3, and 2, 7. Does this set of ordered pairs describe a function? So again, we're looking to see if there are two ordered pairs that have the same x coordinates but different y coordinates. If we have that going on, then we do not have a function. And it turns out we actually do. We have these two ordered pairs here, 2, 1 and 2, 7. We have the same x value of 2 going to two separate y values, 1 and 7. We cannot have that if we have a function, so therefore this set of ordered pairs does not describe a function. And we can just say no. The next way we're going to determine if we have a set of ordered pairs is by looking at a map. Now, perhaps you've seen these things before, maybe you haven't, but a map really just shows some elements, that's what these black dots are, in a set, capital A, and the arrows show what element in B that these guys get mapped to by this relation R, or whatever name you would want to call it, but I'll call it R. So, does this map here describe a function? Well, again, we have a function if each input is sending to only one output. If we have one input being sent to two different outputs, then that is not a function. So in the context of these arrows here, if we had two arrows going from one dot here to two separate dots here, then that would not be good. Then we would not have a function. As long as there's an arrow going from one dot here to one dot here, that's fine. And we see that that is what we have happening. Each of these guys here gets sent to one and only one guy in this set B. So yes, we do have a function here. And lastly, to determine whether or not we have a function by just looking at the graph, we have a special test that is associated with analyzing graphs to determine functions. You have probably all heard of this test. It is called the vertical line test. So you're given the graph of a relation, and here is how the vertical line test works. Draw vertical lines anywhere through that graph, anywhere on the coordinate plane. If each vertical line intersects the graph of this relation at one point at most, then the graph is that of a function. Then your graph is the graph of a function. If you have even one vertical line that intersects the graph in two or more spots, then that is not the graph of a function, you do not have a function there. So here I've provided 3 graphs here of some relations. The question is which ones are functions and which ones are not. So let's take a look at this first one here. So let's use our vertical line test. Let's draw vertical lines anywhere through here that we wish. We can keep drawing lines here, but we have already shown many cases where we have a vertical line that is intersecting the blue curve here in more than one point. There and there, there and there. There's many vertical lines that would intersect the blue curve in more than one place. Therefore, this guy is not the graph of a function. Second one here, let's draw vertical lines. Trying to do our best to keep these vertical here. But we can see for each of these lines in green that we drew, the green line is only intersecting the blue curve in at most one point. So this second graph here is indeed the graph of a function. Try the third one on your own. Should not be too hard, should not take too long to arrive at the appropriate conclusion, but nonetheless, try it on your own. Use the vertical line test to see if this thing is going to be a function or not. So press pause, try this on your own. Once you think you have it, press play and let's see if you are correct. All right, so hopefully you found that the answer was no. That is not the graph of a function. For several vertical lines, each line is intersecting this yellow to orange curve here in more than one point. So these are how we determine whether or not we have a function, either by looking at the graph, by looking at a map, or by looking at a set of ordered pairs. By far, the two most common ways you would be asked to identify a function would be with a set of ordered pairs or by looking at a graph. We don't typically do much with maps, but just wanted to show you that there is another way that you can do it. We can determine the domain of a function by looking at a map or a set of ordered pairs or by looking at the graph of it. But how about just the function itself? Just looking at the symbols, the terms involving x's and everything else, how can we determine the domain of a function just by looking at the function itself? So given the function f of x, we determine the domain by the following process. Step 1, you're going to begin with all real numbers. You're going to start off by thinking, okay, for now, and I stress for now, the set of all real numbers is a possibility. Step number 2. In this step and in the third step, this is where we potentially take x values out. This is where we potentially find guys that cannot be in the domain. So step 2, if your function is rational, that is to say there's a fraction in it, then you have to find and omit all x values that make the denominator of the fraction equal to 0. we saw several examples of rational quantities or rational expressions from previous videos. So again, find and omit all x values that make the denominator of the fraction equal to 0. Step 3, if your function contains a root of even index, then you want to omit and find, first, all x values that make what's inside of the radical negative. We can't take the square root or fourth root or any even root of a negative number. That would give us a complex number, and we're concerned about real numbers, real valued things here. So if you have a square root or a fourth root or just a root of even index, take what's inside of that root, set it to be less than 0, and then solve for x. Those x values that you come up with then, you have to omit those guys. You have to throw those guys out. So we'll see now a couple samples here as to how we identify the domain of some functions. Some functions that we'll be working with more as we get later on in the course, as well as some things that we'll be working with in the fairly near future. And these examples are certainly among the hardest type of thing you would see from me. These are on the more challenging scale. So if these make sense to you, then you should be doing pretty well with the general concept of finding the domain of a function. So first up, we're going to determine the domain of f of x here, 4x plus 7 divided by x squared plus 6x plus 5. So again, step 1, begin with all real numbers. For now, we think, okay, every real number is a number that we can plug into this thing. Next, we move on to step 2. Is there a rational quantity in this function? Is there a fraction inside of it? Well, yes, there is. The entire function is a rational quantity. So we need to find the values of x that will make the denominator equal to 0. Once we find those x values, we're going to take those guys and we're going to throw those guys out. So, as we said, f of x is rational, so we omit any x values that will make x squared plus 6x plus 5 equal to 0. Luckily, we can factor this. That breaks down into the factors x plus 1 and x plus 5. Set each of these factors equal to 0 on their own and solve for x, and we get negative 5 and negative 1. So these two x values we have to throw out. These two guys are gone. Step 3. Does our function contain a root of even index? Again, square root, fourth root, sixth root, 10th root. No, there's no roots happening in here, so we don't have to worry about step 3, and now we're done. So now we can state what the domain of this function is. Therefore, the domain is all real numbers except these two, except negative 5 and negative 1. If you don't want to write it out in words, if you want to write it using interval notation, that would be negative infinity, comma negative 5, union negative 5, comma negative 1, union negative 1, comma positive infinity. For your homework or quizzes or tests, you may have to write things using interval notation, but if you are handwriting something and you're going to hand it in to me, I'm not very picky as to which one you use. So that one wasn't too bad. This was a nice display of checking with of trying to find the domain of something rational. We're going to add another little twist in our next sample problem. This is the most complicated type of thing you could see. We're going to determine the domain of this function, 8 divided by the square root of 5x minus 3. Again, step number 1, begin with all real numbers. Step 2, is there a rational quantity in here? Is there a fraction happening? Yes, there is. Once again, the entire function is rational. So we need to find the x value or x values that make the bottom equal to 0. Well, if the square root of 5x minus 3 equals 0, then by squaring both sides, that means 5x minus 3 has to equal 0. So I want to find the value of x that is going to make this thing equal to 0. Now, I'm not going to do that quite yet, and you'll see why in just a few seconds. I know that step 3 says that if I have a root of even index, I have to omit any x values that make what's underneath our root of even index negative. We do have a square root happening here on the bottom of our fraction, so I need to find also the x values that make 5x minus 3 negative. And whatever x values make 5x minus 3 negative, we're going to omit those guys as well. So instead of doing this in 2 separate steps, we're going to take care of both steps 2 and 3 all in one fell swoop. And what we're going to do is we are going to find the x values that make what's inside of our radical equal to 0 as well as less than 0. So I'm setting 5x minus 3 less than or equal to 0. And it's pretty straightforward to solve for x now. X is going to be less than or equal to 3/5. So these are the x values that we have to throw out. Once again, this may have been a little confusing, so I'll just restate why we did this the way that we did that. Why did we have to know where 5x minus 3 was equal to 0? We had to know that because 5x minus 3 equaling 0 means that we have the square root of 0, which is fine. But then we have 0 in the denominator of our fraction, and 8 over 0 is something we can't have. As a friendly reminder, we cannot divide by 0. That breaks the internet. Things blow up. Just no good overall. So that's why we had to omit the x value that makes this thing right here equal to 0. Why do we also have to omit the x values that made this thing strictly less than 0? Because if there's an x value that makes this less than 0, then we have a negative number underneath a square root, and we cannot take the square root of a negative number. That gives us something complex. We want real valued things. So that's why we did what we did. And we combined these 2 separate steps into one step, making our lives a little bit easier. So to wrap up this problem here, these right here are all the x values that we have to throw out. We can't have any x value less than or equal to 3/5, which means the domain is all real numbers greater than 3/5, or in interval notation, 3/5 comma, positive infinity. Lastly, to finish off this video, recall that in the previous video we talked about finding intercepts. When we had to find the x-intercept, we said that we set y equal to 0 and then we solve for x. Well, now that we're talking in the context of functions here, and we typically replace the letter y with this f of x thing here, you are going to replace the f of x with 0, and then you're going to solve for x. So it's still the same thing that we're doing. It's not a completely new method. It's just a little bit of a notational difference, and just something I want you to keep in mind. Don't get confused by it. It's not something that you should get messed up on. We're doing the exact same thing. So that concludes this video on relations versus functions. How do we know when a relation is a function? By looking at maps, sets of ordered pairs, or graphs, as well as finding the domain of functions. If you have any questions or comments, guys, please be sure to reach out to me. Send me emails, send me questions, text me questions, text me comments, fire something at me, whatever you have to do. Otherwise, until the next video, take it easy, folks.